Hi, now I discuss about how to solve beam in Matlab. So this is the problem that I will solve in the Matlab. Let's introduce it. This is the node, node number 1, node number 2. I make this thing as a node to define the load condition and the moment. And this is node number 3, node number 4 and node number 5 here. And again, as there is a load, it will be easy to define if you define this is a node, this is a node, and the element is here. There is one element, two, three, four, and then there is elastic properties and there is I. So let's go. uh, this is my main file. So when I run it, you see here the force are in here, and it say that the resulting beam to truss. So let's go. The result are printed in here. You see here the uh, vertical force at y direction in here, vertical force at F2 there, that means here there are the two vertical force and M1 M2, M1 and M2. I get it from here. So how can I get it? Let's go to some theoretical thing. So first we have to form a stiffness matrix depend on the beam condition. I mean, you know how can form the stiffness matrix, and these by this thing we form the stiffness matrix in here mainly on elastic modulus and moment of inertia and length. And in the short form, it defined like this way, where there is the there is the W1 means its displacement here, W1 displacement, W2 means node number 2 displacement, W1 means node number 1 displacement, and theta 1 means at node number 1 rotation, and theta 2 means node number 2 rotation, node number 2 rotation, and fy1 there and fy2 is there, m1 is there and m2 is there here, and in short form there is here. So let's go to the main file. So I divide the program into 3 or 4 files, and I got this code from a book. It's called Introduction to Matlab and Abqus, and this is the main file. So let's go. How can I define in here? So here number of nodes, you see here number of nodes 1 2 3 4 5. Number of elements is 4, 1 2 3 4, and number of nodes per element. I mean, if you take one element, this element, there is a two nodes, 1 and 2. Again for element number 2, there is two nodes, 2 and 3, and number of degree of freedom per node is 2, and there is the geometric connection. For node number 1, its coordinate is 0 0. For node number 2, its coordinate x coordinate is 400, I mean is millimeter, and again for node number 3 it will be 4 plus 6 10, so 10,000 millimeter. And you see here first I take the zeros, I mean I make the matrix zeros, so there is no x value, only one column. You see here, if I want to, if I show you here, you see zeros and ending, that means number of node is 5. So this matrix is 5 rows 1 column, 5 rows 1 column and zeros. And then connectivity matrix. So connectivity matrix again, uh, it depends on the element. So element number 1 connect to element number 2, and 2 connect with 3, 3 connect with 4, 4 connect with 5. And there is properties, so it depends on the number of element. So here two properties, one property is elastic modulus and one property is moment of inertia. So I define in here according to this. And then boundary condition, number, this is nodal freedom. So nodal freedom is always is 0. And there is hinge condition, it is in here. And joint load in here, node number 2, the joint load is 20 kilonewton. And then there is also moment in here. You see, define joint load into 2, number of node and 2, and makes other joints is 0. And there is node number 1, and on the x here, x coordinate I define the vertical load, and y coordinate I define the moment here. And then number of when we go to node number 4, there also a vertical uniformly distributed load, and I define the uniformly distributed load like this way. So go to the main file, again main file, here I call this file beam to data, this file. And this file, this is global stiffness matrix. Let's go there. I talk about this matrix. Mainly they define this according to the G. So let's go G here, global connectivity matrix, node number 1, node number 2, and the connectivity matrix is in here. And there is it's called element stiffness in local coordinate. So here uh, I define in here K1, KL. It depends on the number of condition of hinge. And this is the local matrix. So I define the local matrix in here. And this is the force matrix, global force vector. So I define this global with this coordinate. And this is the K matrix, and I call this K matrix force matrix and free beam. And there is some logic in here. After that, when you solve, you can get the thing in here from here. So if you need the code, please comment on my video and subscribe my channel so that I can give you the code. Thank you for watching my video. Okay.